Hello students, here is a quick review on simple harmonic motion, oscillations. Now you got to listen to all that I say very clearly and try to take notes because there are 10 questions just from this chapter. So first of all, what are the conditions for simple harmonic motion? Now, let's take the best example for simple harmonic motion, which is a spring with a mass attached at one end, and you pull it down just a little bit, and the mass goes up and down. Now, if you study the motion of the mass, you see that the acceleration of the mass is always towards the mean position. The mean position is the resting position before you pulled it down. So that's the first condition for simple harmonic motion. The acceleration is always towards the mean position. The second condition is that the acceleration is proportional to the displacement from the mean position, which means that the further it is from the mean position, the bigger its acceleration is. So where is the acceleration maximum? The acceleration is maximum at the amplitude position. Where is the acceleration minimum? The acceleration is minimum at the mean position or the equilibrium position. In fact, the acceleration is zero at the equilibrium position. So those are the two conditions for simple harmonic motion. The acceleration is always directed towards the mean position, and the acceleration is proportional to the displacement from the mean position. What do you mean by frequency? Frequency is the number of oscillations in 1 second. The number of oscillations in 1 second. So, if there are 30 oscillations made in 1 minute, what is the frequency? 30 oscillations in 1 minute. That means 30 oscillations in 60 seconds. So how many oscillations in 1 second? 30 divided by 60, which is half or 0.5. The unit of frequency is hertz. So the answer is 0.5 hertz. Frequency is the number of oscillations in 1 second, and its unit is hertz. Time period. Time period is the time taken for one oscillation. So in my previous example, if it makes 30 oscillations in 60 seconds, then what is the time taken for one oscillation? It's 2 seconds. 30 oscillations in 60 seconds. Time for one oscillation is 2 seconds. So now you see that frequency is the reciprocal of the time period. So T is 1 over F. That is the relation between frequency and time period. So I may not be writing everything, but you got to be listening very carefully to what I say. Then, here is the formula for time period of oscillations of a loaded spring. Well, this is the formula for time period of oscillation of a simple pendulum. Again, this is the time period of oscillation of a simple pendulum. T is 2 pi square root, where L is the length of the pendulum, it should be in meters, and G is the acceleration due to gravity. Now, you know what a simple pendulum is? It's a string with a small mass attached to one end, and you pull it to one side, it begins to oscillate. So the question now is, does the time period depend on the amplitude? Does it depend on how far you pull it? Well, for a small number of oscillations or for a small amplitude, that time period is independent of the amplitude. So whether you make it small or whether you make it big, the time period does not depend on the amplitude. Second question is, what about the mass attached? Do we have the mass in the formula? No, we do not. What does that mean? That means that whatever mass you have, whether it's 100 gram or 200 gram or 1 kilogram, it does not affect the time period. So if I ask you a question saying, if the mass is doubled, what happens to the time period? The obvious answer is nothing happens. The time period is independent of the mass. Now remember that in practical cases, if you have a big mass, air resistance is going to affect the motion of the pendulum. But here we are talking in an area where there is no air resistance. Or in other words, we are ignoring the air resistance. So that's the time period of a simple pendulum. We will come back to this later. But for now, let's look at the formula for time period of a loaded spring. T is equal to 2 pi square root m by k. M is the mass attached to the end of the spring, and k is the spring constant. Sometimes it's called the force constant. So here you can see that the time period does depend on the mass attached to the spring. But next question is, does it depend on the mass of the spring? The time period in this case is independent of the mass of the spring because we are talking about light springs. So this formula is only applicable to a light spring. And that's all I'll ask on the exam. What about the force constant? What do you mean by force constant? It's the tightness of the spring. A tighter spring has a bigger force constant. And if the force constant is bigger, then the time period is smaller because the force constant is in the denominator. So if I ask you a question like, what happens to the time period if the spring constant is increased 4 times or quadrupled? Spring constant is increased 4 times. What happens to the time period? Your answer would be the time period becomes half. Where did I get that from? You see that the spring constant is under a square root. Square root of 4 is 2. And since the 2 is in the denominator, the time period becomes half. Because if you increase the spring constant, time period decreases. Here is a related formula for spring constant. Here F is the force applied at the end of the spring. K is the spring constant and delta X is how much the spring stretches. How much the spring stretches. So again, we'll come back to this formula later to work out one problem. Or let's just do it one at a time. Let's do one problem each using each of these formulas. So the mass of a pendulum is 1 kilogram. And find the acceleration due to gravity on a planet where the length of the pendulum is 1 meter, and I'm going to give you the time period as 0.5 seconds. So first of all, you recognize that the time period here depends on the acceleration due to gravity. So which means if you take it to a planet with a higher acceleration due to gravity, then the time period will become smaller. So this question, the mass of the pendulum is given. Is there anything to do with mass in this formula? Nothing. So that's just given to throw you off. So we need the length of the pendulum, which is 1.0 meter, and we also have the time period. I should have said if a 1.0 meter long pendulum has a time period of 0.5 seconds, okay? So how do we work this out? T is 0.5 seconds, the length of the pendulum is 1.0 meter. The formula is T is 2 pi square root L by G, but we are trying to find G, so let's square both sides to get rid of the square root, and then rearrange it to get G as the subject. You get 4 pi squared L by T squared. That's it. Plug in the value of pi and remember to square it. And then the length is 1.0, it's in meter, that's all right. And time is 0.5 squared, time period that is. And you get 158 meter per second squared. You know, that's a very big value for acceleration due to gravity. This is a hypothetical planet. I just threw in the numbers and that's what you get when you do that. But anyways, I hope you understood how this problem has been worked out. Let's now move on to a problem using the time period of a spring. So now you see that the 1.0 kilogram mass is attached to a light spring. It's a light spring because we do not consider the mass of the spring, and this formula is only applicable to light springs. And it undergoes simple harmonic motion of period 2.0 seconds. What is the spring constant? So what is the spring constant? K. What's given? Time period is given as 2 pi square root m by k. That's the formula. Since we're looking for k again, you got to square both sides. So you get t squared is 4 pi squared m by k squared. M by k, I mean, the square root vanishes. Make k the subject. So that's 4 pi squared m by t squared there. Plug in the numbers. It's 1.0 by 2.0 squared multiplied by 4 pi squared. And that gives 9.87 Newton per meter. That is the unit of spring constant. 9.87 Newton per meter. Now let's talk about the acceleration in simple harmonic motion. I think I already spoke about that, but we'll try to correlate both acceleration and velocity. So you have the spring and it's moving back and forth horizontally between the amplitude positions B and C. So B and C are the extremes to which it can go, so that's why it's the amplitude, and A is the mean position because it's right in the middle. So the mass goes back and forth, and we want to talk about acceleration. The acceleration is maximum at the amplitude position, but the velocity is minimum. In fact, the velocity is zero. Why? Because the mass has to stop just before it returns. That's why the velocity is zero. Do you see that? So where the acceleration is maximum, the velocity is minimum. But at the mean position, it's exactly the opposite of this. Velocity is maximum, but acceleration is now minimum and it is zero. So see how the relation is. Acceleration is minimum at the mean position, while velocity is minimum at the amplitude position. Acceleration is maximum at the amplitude, while velocity is maximum at the mean position. Since we have already talked about velocity, we can now talk about the total mechanical energy. We know that there are two parts. The moving mass has kinetic energy, but the spring has potential energy because you're stretching it. And when we talk about total mechanical energy, it is the sum of the potential energy and the kinetic energy. And the formula is 1 half K A squared, where A is the amplitude, K is the spring constant. So you got to be careful on this formula because there is a square on the amplitude. So let's say that A is the amplitude is doubled. What happens to the total mechanical energy? It is quadrupled. That means it becomes 4 times because 2 squared is 4. What happens if A is tripled? 3 squared is 9. So the total mechanical energy increases 9 times. Quite simple. So depending on the question, you look at the formula and try to answer accordingly. What happens to the energy if the spring constant is doubled? The spring constant is K. There is no square on it. So if that is doubled, then the total mechanical energy is also doubled. That's it. So try to break down the formulas. Try to look at each term. Look at if there's a square on it. Look at if there's nothing on it and then answer accordingly. Or if that formula doesn't have a quantity and I'm asking you about how that quantity affects it, you say it's independent. It's not going to change. All right? So that is how you answer questions. Remember, this is just the first part. You're going to have 4 parts at least in the review. So make sure that you listen to this multiple times and understand where I'm going with this. This review is on just simple harmonic motion. Thank you.